Okay, good evening everybody. My name's Mike Wright and I'm very pleased to be able to welcome you on behalf of Lancaster University to this 50th anniversary lecture. And we're very pleased to have Roger Kemp here to give it. I've just got a very brief bio of Roger to tell you. He tells me he's not a real academic, but he's actually been here for 12 years, I think he says, which is real enough for me. But he spent many years in industry working on transport projects before he came here. And since he arrived at the university, he's been heavily involved in energy policy, particularly transport energy, and the impact of low carbon policies on the electricity system, obviously related to what he's going to talk about now. And he's a fellow of the Royal Academy of Engineering. I've been asked to give a little plug for our new engineering building, which many of you may have noticed, very close to here. Engineering is one of our key expanding departments, and so that's why we've got a new engineering building, which is all fancy, looks wonderful, and is going to do all sorts of things for both teaching and research in all sorts of fields of engineering, which are too numerous to mention. But getting back to Roger, today he's going to talk to us about how we can reduce our energy consumption in order to avoid the worst effects of climate change. So, without any further ado, I'd like to hand over to Roger.
Thank you very much. Well, good evening, everyone. One of the most important parts of this opening slide is the question mark after Save the Planet. Some of the publicity that went out for the lecture failed to mention that question mark, and I see that as being a vital issue, but we'll come back to that in a bit. Some lectures are very much structured along the lines of a lot of sequential sets of information that comes out with an obvious conclusion at the end. The obvious conclusion might be you have to scrap your car or vote Conservative or whatever else. In this case, it's not like that. What I'll be doing is talking about some of the issues you can see on the slide behind me, and then at the end I will try and pull these together, but there's not going to be a nice clean answer, because I don't believe there is an answer. The key points that I'd like to get through in this lecture, firstly, sources of low carbon energy, what they're good at, what they're less good at. Secondly, how we're going to deal with transport without carbon dioxide, and that's really challenging. And even more challenging, how we're going to heat our homes without burning gas. So let's see if we can get through the whole lot in about 45 minutes, and then I'm only too happy to have a provocative discussion at the end. Most of the facts, so as they are in the lecture, are based on work I've been doing over the last sort of 10, 12 years. These are reports. If you look on the website, you will find references to them. They're all available, mainly from the Royal Academy of Engineering, sometimes from the Institution of Engineering and Technology. But that's basically where the information has come from and where the detail can be found. I'd like to start by the energy trilemma. Is trilemma a familiar word to people? Well, you know what a dilemma is? It's sort of two choices. A trilemma is basically where you've got three things and they're all basically incompatible. So what we're trying to do with energy policy, firstly, is to establish affordability. If people can't afford energy, then quite obviously governments are in a mess, as we've discovered. Security of supply, even more serious for politicians, is keeping the lights on. And finally, the commitments we've made to the Climate Change Act. Now, this is actually quite a serious commitment. We're talking about an 80% reduction in CO2 by 2050. That's only, 35 years away. And remember that generating plant generally lasts 40, 50 years and takes 10 years to build. So we're not in a situation where we're looking at long term. We're looking at things that have got to happen soon and that are very relevant to this whole sort of problem. I thought it'd be useful to put up a number of graphs to begin with, just to try and set the scene. And this one comes from the Academy's report, Generating the Future. And it shows on the left the supply of energy, and on the right the demand. And as you can see, the figures incidentally of 2008, which is when the Climate Change Act was passed, that at that time biomass renewables were basically pretty tiny. The big supply of energy was fossil fuel, and that's this black lot along the bottom here. And the two parts of that are particularly interesting: transport, mainly petrol and diesel going to road vehicles, heating, the gas, the grey part. And if we're going to have any hope of meeting our 2050 targets, then we have really got to find some way of dealing with those two big issues. When you start looking at home energy use or domestic energy use, you can see from this graph that the big issue is again gas heating. This blue bit here, bright blue on my screen, rather dirty blue on yours, that's gas being used for space heating, that's gas being used for water heating. And unless we can find a way of dealing with that, then we're not actually going to manage to reduce emissions. Unfortunately, people don't take energy nice, cleanly and smoothly at a constant level. The previous graph, that one, was talking about average powers over the year. Here we're looking at what happens during the day or during the week. And I've plotted here two graphs. The top line is February 2010, when it happened to be quite cold. And the one below it is July 2009, when it was actually quite hot. And you can see that the total power supplied on the electricity grid varies between about 20 gigawatts. I won't do that, sorry. 20 gigawatts, which is the minimum we have during the summer night, and about 55 gigawatts, that's the maximum during winter, particularly at about 6 o'clock in the evening. And this is quite a challenge for grid supplies, that we're looking at more than a 2-to-1 ratio in demand. But if you think electricity is difficult, wait till you see gas. This is the demand for heat. And the blue bit along here, that sort of muddy blue there, that's basically the electricity demand you've seen on the previous slide, so that's that. And here it is over the entire year period, it's for 2010, and you can see that it varies between about 55 gigawatts at the top down to about 20 gigawatts at the bottom, as in the previous graph. But we've now got heat on the same graph, and you can see that that goes up to somewhere around 300 gigawatts instantaneous demand in winter. And this is where we have a really serious issue, that it's not just a question of saying, how do we get so many kilowatt hours or megawatt hours or whatever it is throughout the year? It's how do we deal with these short-term peaks in power and peaks in demand? And part of the solution is going to have to be low-carbon electricity. I'm sure we've all seen lots of information about different forms of low-carbon generation, about solar panels, about wind turbines of various sorts, different forms of tidal energy, and of course nuclear power stations. This is Hisham A, Hisham 1. But they all have issues. A lot of the flow renewables, this is wind, tides, tidal currents, and sun, are not there all the time. The graph on your right shows the output from wind turbines over winter of 2008 and 2009. And you can see there that for a fortnight we didn't have any appreciable wind. Now we looked at this as part of a study done in the academy, and for a lot of the really serious periods of lack of wind, it's an anticyclone over pretty well the whole of Northern Europe. So saying, okay, we'll just connect into Scandinavia or something doesn't actually help. And that's a fairly serious problem. One can live perhaps with a few hours of missing electricity energy. To go for 2 weeks without electricity is actually very difficult. So how does one actually match the various sources that we're talking about with what we actually need and with the demands we have? Nuclear power is more consistent, but nuclear power is actually very good if you switch it on and want to leave it on. Nuclear power is pretty poor at following the sort of sudden demand increase that we get in Britain at about 7:30 in the morning, when everybody wakes up, puts on their heating, puts on their kettles, sets off their gas boilers, has showers, and all that sort of thing. So it's great as a steady load. It doesn't make much sense as load following, and it certainly doesn't make much sense as peak lopping, peak where you just want it for a few hours in winter, because nuclear power is expensive, and to build expensive power stations that you're not going to use for most of the year doesn't sound a very good investment. There's been quite a lot of talk over the last decade about biofuels. I think the general consensus now is yes, they're great, but we don't frankly have enough land to make an appreciable difference. One can perhaps say, yes, we can get to 10% biofuel in our liquid road transport fuel. We could perhaps use biofuel just for aviation if we didn't use it for anything else. But the idea that it would actually replace gas, coal, oil in our mainstream heating, generating and transport uses is really most unlikely. There are various other options that you can think about. If you go to Sheffield, you'll find this district energy network, a brilliant network, pipes under the city centre, burns 200,000 tonnes of waste per annum, which means you don't have to have landfill sites. It provides heat for 150 big buildings, some of them are quite large university buildings, hospitals, city offices and so on, and provides electricity equivalent to about 22,000 homes. But what are the constraints? Why don't we all do it? Well, one of the first problems is that you want somewhere that's relatively compact. It works quite well in Sheffield, where there are a lot of buildings fairly near the centre. It would work rather less well in spread out places like, I don't know, Prestbury or Wilmslow or something, where houses are further apart. In all the successful cases throughout Europe, district heating has relied on the local authority having the enthusiasm and having the incentive to actually make things happen. At the moment, most local authorities, particularly in the compact cities, are saying that they're on the verge of bankruptcy. If they have difficulty in actually meeting their legal obligations, how many of them are going to consider that building combined heat and power is actually a priority? And it also works best when you don't have competition. If you're going to say, well, we insist on having competition, then that's rather difficult. Also, I think you have to ask a fairly fundamental question. Does it make sense to burn second-hand plastic bags and say this is zero carbon? After all, plastic comes from oil. Shouldn't you really be campaigning to say we don't want the plastic bags in the first place, we will take our reusable raffia bag to go and buy our potatoes or something, rather than getting packaging and then burning it? So I think there's some fairly fundamental questions about what counts as zero carbon in this particular environment. There are also some challenges on renewables, and one is how you control the system. If you consider this as being the overall system as we have at the moment, where you've got some central generators, you've got transmission and distribution grids, and you've got consumer loads. Basically, you have a central marketing dispatching system. This sends demands to the various generators. You have control systems that monitor the frequency and the voltage and that change the excitation and the amount of steam that goes into the generators. So basically, it's a control system based on the centre. If we get to the situation where we have most of our energy coming from distributed generation, this area here, then we have a rather different problem. Here we've still got the central marketing and dispatching, and we've still got the generator voltage and frequency control, but unfortunately it's an increasingly tenuous set of links. And what we're really seeing is the control of frequency and voltage by probably real-time price signals through home energy management, through smart cities, through community groups, through controllable consumer loads, and through distributed generators. And this is going to be quite a difficult challenge for people because we don't no longer have the central control of the grid. And as we've been building solar panels and wind turbines up till now, they're not suitable for a sort of distributed frequency and voltage control. So quite how you work the grid under these circumstances is far from obvious. There are solutions, but we're certainly not doing it, and no one seriously in Britain at the moment is really thinking about it. This is the frequency you see if you clock onto the National Grid website, and you can see it starts at 50 hertz, bounces up to about 50.1, bounces down to about 49.9 over a few minutes, goes back up again. So it's all round about 50 hertz. In Ireland, they've discovered that by having a lot of low inertia wind turbines, this frequency is getting rather more bouncy. The frequency changes more, and this can be quite hazardous to the operation of the grid. So there are quite a lot of technical challenges. It's not just a question of saying, let's buy some renewables and let's bolt it into the grid. one has to redesign the grid to make it work. And we've had 100 years of basically central power stations, and now we're talking about redesigning the grid so that in fact it will take distributed energy, and that's actually quite difficult. There are also some economic challenges. Up till now, we've had a market price that's based really on pounds per megawatt hour or pounds per kilowatt hour, which is closely related to the real cost because the main cost has been fuel. If we have a situation where the cost is dominated by CapEx, capital expenditure, on renewables and nuclear, then to have a market that's based on the operational costs, frankly, becomes a bit nonsense. And if you're not careful, it becomes more like a game of poker, with people bidding to get a slice of this market, prices that are not related to their actual costs. Now, there have been various attempts at electricity market reform and other things, but the general view, I think, is that these might be sticking plasters, and we have a fundamental problem with our overall energy market system. A final interesting challenge for renewable energy is oil prices. That renewable energy looks brilliant so long as oil prices are going up and gas is following. Once oil prices drop, and now they're below around about $50 a barrel, then the financial case for a lot of renewables start looking a bit dodgy. And it's not very obvious how we're going to continue to manage this. So these are some of the challenges. It's not straightforward, and there's a lot to be done. I'd like to digress now and talk about the difference between policy making and personal decisions. Now, it may sound a bit sort of semi-detached from the main purpose of this talk, but I'd like to sort of take you down this little route. Firstly, strategic choice. If you're the government, you might say, how do we reduce CO2? And you could say, well, let's build more nuclear power stations, or we'll subsidise wind turbines, or we'll subsidise electric vehicles, or something of that sort. If you're an individual, you probably don't have those same choices, and you've got, what should I personally do? And sometimes these two don't actually tie up. Let me give you an example. If you commute from Lancaster to Kendal, and you go by one of those trains, you get an emission that's roughly 6 kilograms of CO2 per commute. That's the sort of traditional statistics for that sort of thing. If you were to commute by electric vehicle, you'd probably get 3 kilograms of CO2 per commute. So if you're the government, your policy might be to say, right, what we want to do, scrap diesel trains between Lancaster and Kendal, persuade everyone to go buy electric cars. If you're an individual, then the choice is really rather different, because you can say, well, there's a train going. If I get on it, it will make absolutely negligible difference to how much CO2 it pushes out. So what I should be doing is going by train, even though the train is actually less efficient than the car. But for me, taking my individual car is always going to be worse than for me squeezing into an existing train. So these are some of the sort of difference in issues that what makes sense at national strategy level sometimes is not the right choice at personal decision-making level. And that's sometimes a problem. So, after that minor digression, looking at transport without carbon dioxide, or with a small amount of carbon dioxide. For several years now, we've been working on electric vehicles. There was a big boost in about 1978 when the oil price went up, and various people said this is where it's going to have to happen in future. And then in about 1980, the oil price went down, and everybody stopped working on electric vehicles, and I found myself redundant in an electric vehicle development group. Great if you want a second car or about town driving, and if you don't go any long distances. Most current EVs are about 100-mile range. At the moment, they're not showing evidence of replacing first cars, family cars. And the economics, frankly, depend on the fact that they're not taxed. But you can't imagine the government saying, oh great, everybody's now using an electric vehicle, so we can ignore tax and all that road tax we won't bother with and all the fuel tax we won't bother with. They'll have to find some way of taxing electric vehicles if they really become widespread. And that will rather mess up the economics. There's also, while there's relatively small numbers, it's a pretty limited impact on CO2. But you can do better. This is a dream machine. It's a Tesla, designed originally by Lotus. Top speed 125, 0 to 60 in 3.7 seconds. Jeremy Clarkson would drool over it, and it'll go 200 miles between charging, which is great. Where it becomes problematic is that the 53 kilowatt hour battery requires 8 hours charging at 7.5 kilowatts. Now, the average load of a typical house is about 1.5 kilowatts. So if you had a street full of these things, the local electricity distribution people would know about it. And there'd have to be a lot of digging up of roads and all that sort of thing. So it becomes a bit challenging if everybody says, I want a really high capacity vehicle. Basically, if we're going to meet the 2050 targets, then almost all of our car travel is going to have to be by electric. And the natural time to plug these things in is when you get home from work. But if you remember that previous graph of electricity demand, 6 o'clock in the evening is the worst possible time as far as the grid's concerned. And so we need shift systems that will shift the demand from the evening peak through to the middle of the night at some stage. And I'll be talking a bit about those in a minute. Still on the transport theme, railways are generally held up as being good. In 2007, the Department of Transport published a white paper on sustainable railways, and I did some research for them on how much carbon dioxide different railway vehicles actually put out. I wouldn't recommend this as reading the original report. It's about 90 pages, and it reads like a train spotter's manual. There is a graph. This is a sort of extract from it in slightly bigger letters so you can read it. And as you can see, plane from London to Manchester is obviously the worst in terms of CO2 emissions per person. Interestingly, single and double deck buses don't come out as well as you think they ought to. Electric trains come out much better than diesel trains, and even so, it's not perfect by any means. So railway electrification is good. If you look at those bars there, the green ones, which are the electric trains, are roughly half the emission of the red ones. So diesel train, Glasgow to Manchester, about 35 grams per seat kilometre. Electric train, recently introduced, class 350s, 16 grams at the present mix of electricity generation, down to about 8 grams, probably by about 2030, if we get our act together on decarbonising the electricity system. But what really matters is actually the time of day when you take your electricity. Here I've plotted, I've taken from the web, the data for the 9th of January, that's last month, of the generation by fuel type. Coal, gas, nuclear, wind, and are the 4 main big ones. And as you can see, coal along the bottom is one of the dominant. I was looking up recently, a few minutes ago, what the current state is over the last 24 hours, and coal is still about 30% of our present electricity demand. If you take those two lines and look, one at about 6:30 in the evening, this is the evening of the 9th of January, and one at 11:30 in the evening, you can see that at 6 p.m. the carbon intensity of electricity is 490 grams per kilowatt hour, and the same figure at 11:30 p.m. is only 360 grams per kilowatt hour. Now, as we decarbonise the electricity grid, this will become more emphasised. This is the figure for 10th and 11th of January, and let's assume that we're actually managing to decarbonise. So we've done nuclear along the bottom, renewables next, gas just for the top bit. If you're adding demand in at 1800 hours, you're basically going to be switching on more gas turbine power stations. So the question really is, if you decide as a matter of policy, we're going to switch transport from cars onto electric railways, and the whole of the commuting peak will actually require additional gas turbine power stations, are we actually then saving the sort of CO2 that we thought we ought to be saving? So go back to these figures. Whoops, there. Yes, if we work on average values, but we're not actually working on average values, particularly for commuting. For commuting, we're talking about taking most of our electricity at that point, which would mean having more gas turbine power stations, so the marginal CO2 for the transfer of transport is actually going to be quite heavily carbon intensive, probably about 450 grams of CO2 per kilowatt hour. So this, I think, is a challenge. How do we deal with a situation where we've got not just an average CO2 of the electricity system, but we're having to add particularly certain types of generation in order to cope with the additional loads we're putting on as a way of decarbonising transport and heating? I was surprised when I did the calculations about buses. When they're full, buses are always lower CO2 than travelling by car. But if you look at the data on buses, and I went to talk to Stagecoach, they reckon they're about 6 miles a gallon. It's around town, it obviously depends a bit on where the bus is going. I was surprised to read that the average loading is actually only 9 passengers. Now, Stagecoach in Lancaster couldn't tell me that, but I did go and talk to the passenger transport authorities in Manchester and Liverpool, and at the time they said, okay, it's a few years ago now, that 9 was about the sort of typical number of passengers. Every bus we go on, it feels much more full than that. But then that's because we go on the full ones, because we go at peak times. If you look out of your bedroom window at 6:30 in the morning and watch the buses going to the university, there are not very many students on them. And I think this is part of the problem, that if you want buses to be attractive, you have to do a regular service throughout the day. If you want to reduce carbon, you say, well, no, not going to run any buses except at peak. And this is, I think, a difficulty of any of these passenger transport operations. There are battery buses. There's a French bus there, ideally suited for replacing short routes like going around the Marsh Estate or somewhere, and could very well be used and could charge in the night and could provide transport during the day. Should we perhaps be bringing back trams? If you go to most continental cities, trams are common. We had trams in Lancaster, at least according to Wikipedia, which is a not entirely notorious, reputationable sort of perfect source, but according to that, it was January 1903 to April 1930. And one could ask, is there really time for a reprise? Should we be looking at this? Now, this gives you an electric bus, but I think one has to ask the question, is it better to go to a tram or to a battery bus? A battery bus you can charge up at night, you can spread the load. A tram, invariably, you'll be taking the load when people actually want to travel, which tends to be at peak periods. A really good way of running transport is to use hydrogen as a means of storage. Low tailpipe emissions in city centres, which is great. A bit less efficient than electrification, but if you're making the hydrogen by using surplus wind energy in summer, storing it and then using it in the winter or using it at peak periods, doesn't matter what the efficiency is. If you're building plenty of renewable energy supplies in order to provide heating and other uses, then you will probably have surplus electricity and surplus zero carbon electricity in summer, and it would therefore be good to try and find a way of using that. And hydrogen offers one way of doing that, a very worthwhile study. The title of the lecture was about replacing your car. And as you know, cars are becoming more efficient. Here's a graph that I couldn't find figures beyond about 2012, but this is from 1997-ish down to 2012. And as you can see, for diesel cars, the fuel consumption has dropped from about 7 to about 5 litres per 100 kilometres, and petrol cars is just a bit worse. A few years ago, one of our students, Esther Dudek, did an analysis to say, should I scrap my car and buy a new one before the thing's actually fallen to bits? And she did this graph. If this is the improvement in fuel use along the bottom, this is the balancing distance you have to drive before you've actually saved as much fuel as it took to make the car. So if you're only getting a 10% improvement in fuel use, you've actually got to drive 150,000 kilometres before you've counteracted all the additional energy that went into scrapping the old car and building a new one. And she started off with a 1990s Ford Escort, as students are wont, and said that, well, okay, that's what if I buy a 1.6 Ford Focus, it goes there. If I buy a Honda Civic, I could get to there. And if I buy the cheapest possible, lowest emissions, lowest fuel consumption Citroën diesel, then I sort of break even after 30,000 kilometres. But I think this is quite an interesting debate as to how much saving you need to make before you can say, I will scrap this existing asset and produce a new one, get a new one. And the same argument actually holds true for housing. Because if you're going to say, let's demolish inefficient housing, you can do exactly the same sort of calculations there. Should I be demolishing inefficient housing and building more efficient housing? Should we avoid mail order? If you've got a situation where you can either drive into town and go to a shop that seems to think that its mission in life is to warm Penny Street by having its doors wide open in January, or alternatively you can get it delivered by the post office from some central place, then probably you're better off getting it delivered by the post office. If, on the other hand, you do a lot of searching for something using Google, and their servers use about 250 megawatts, and then that's about a quarter of one of the Heysham power stations, and you then go into somebody else's server, so there's plenty more megawatts being used there, then you start asking, well, where's all this energy coming from? And if it's then delivered by a whole fleet of different types of vans from different types of companies, this doesn't make much sense environmentally. Environmentally, perhaps the best solution would be to say we'll go back to having post office parcels monopoly. Politically, not very acceptable, at least not with the present arrangements. Might be so in Greece, but that's different. But the competition by itself does tend to increase energy use, both here in this example and in some of the other examples one could look at, like, for example, heat networks or some electricity networks. The ideal, as I'm sure everybody here knows, is cycling. But frankly, cycling in Lancaster, particularly in December or January or February, wherever we are now, isn't really very much fun. Okay, we've got some nice cycle tracks, perhaps not quite as awful as those in various parts of the Lake District where they're actually intentionally overlap with the roads, but they're still a bit scary in places. And certainly unlike some Scandinavian cities where to park on a cycle track is absolutely forbidden, and even to put your skip on a cycle track temporarily would be forbidden. So I think yes, cycling is obviously, you can't get better than that, other than perhaps walking, but I'm not sure that Lancaster has quite got their brain round how you produce cycle tracks. The third big area I wanted to talk about was how we heat homes without burning gas. Now, some houses are designed new and work well. This is Lancaster Co-housing out in next to the Loon. It's built to what is called passive house standards, where they have excellent insulation and air sealing, triple glazing, and most importantly, forced air circulation. So rather than just opening the window and letting all your air that you've warmed by your computers and your fish fryers or whatever go out through the window, you circulate it through a heat exchanger, so you warm the incoming air as you cool the outgoing air. It works. They basically only need heat very, very rarely, and for domestic hot water. And it was won an award. This is their boiler house. They have a wood chip boiler there, and this provides heating for hot water. It can run all day if it wants to, and there's a big storage tank there that stores the hot water. So it works. If we demolished everything else, built all houses like this, we could drastically cut the energy we use for heating. With existing houses, yes, you can heat things, and if you talk to the various government departments, they talk about grants for cavity wall insulation, or loans nowadays, I think, or putting roof insulation in. And the pictures you see are always like this. These are a couple of commercial pictures showing how easy it is. If you go into any sort of normal house, one that's got little turrets and garrets and big windows and stone walls that don't have cavities and so on, it's actually quite difficult to heat a lot of houses. And even quite a few modern houses from the 1980s were designed not primarily to be easy to heat, because they were designed from the days when oil was sort of $10 a barrel, and it seemed a good idea just to burn it. One can do things. One can use heat pumps to replace gas boilers, basically like the same mechanism as a fridge. It pumps heat from outside to inside in the same way as the fridge pumps heat from inside the fridge to the coils at the back. If you don't like one of those outside your window, you can have a ground source heat pump that's probably more efficient, and you merely dig a small trench in your garden and put in a plastic pipe, and it takes the heat from the ground and puts that into your house. But the limits. If you happen to live in a nice, spacious house, this makes a lot of sense. If you've got a spare £25,000, this makes a lot of sense. If you live in a flat, a ground source heat pump doesn't work too brilliantly. Well, it might if you actually went into your neighbour's house down there, but they might complain. If you've got a house that's well insulated, you can run your heat pump all day and every day. If you haven't got a well insulated house, then you're still using your electricity at peak times, and that is exactly what we don't want to be doing. Solar water heating, again, if you can do it, great, but it does require a storage tank, and the majority of houses nowadays are being built with combi boilers without storage tanks. If you've got neighbours who bought a house which had trees planted in its garden about 30 years ago and which are now getting far too big, and they regularly cut them down, then having a fire that burns their waste timber is actually very good. Environmentally, it's a bit less good if you import it as wood chip from Canada, which I think is what they're doing in the Drax power station conversion. Also worth remembering that a lot of urban houses don't have storage space. You need about a cubic metre or at least for storing the wood, and quite a lot don't have chimneys, and there are various issues. Talk to Barbara Mayer in this in LEC, and she'll talk about PM10s, particulate matter coming off burning these types of fuel. And there isn't basically enough waste wood to go round. So I suppose this is really the summary of the challenges. We can't insulate all homes to passive house standards. Knocking everything down and rebuilding becomes expensive and also would use a lot of energy its own right. Peak heating load is already many times the present grid capacity. Even if we use the best type of heat pumps, we've still got quite a big peak heat load that it's not very obvious how we work it, and we'd need it mainly in winter, so the economics of the electricity system become rather unattractive if you're building power stations that you say to someone, please build me a power station, oh, and by the way, we only want it from November to March. The economics of that are not particularly brilliant. So perhaps we can do something with smart controls. This is moderately smart controls, and it's what we did to our house. This up here is a living room that's only used in the evening, so we put in various sort of tablet computers that are linked to radio-controlled solenoid valves and all that sort of stuff. And now our living room comes on just from 6 o'clock in the evening till 11 o'clock, goes off the rest of the day. Bedrooms come on when we want them. So basically we've, rather than switching on the house and saying we heat the house, we say we heat the areas we're living in. And it has reduced electricity and gas use, particularly gas use. You can see seasonal consumption's gone down by about 30%, despite the fact we're actually using the house more. So probably comparing like with like, by insulation and so on, we've reduced it by 40%. This is by 40%, it's not by 80%. And so to get 40% possible, to get 80% reduction by these means is actually pretty challenging. And that perhaps is where we get smart grids. And this is where we try and integrate everything. This is the sort of ultimate, I mean, if you've seen the recent films, this is where the sort of the theory of everything comes together in the smart grid. The idea, very simple. You have electricity meters, you have gas meters, and they connect into a consumer display. And the original idea was that people would just look at the display and say, oh dear, we're using a lot of electricity, perhaps we ought to turn the taps down a bit. I suspect that sociologically people probably wouldn't do that very much. It becomes more interesting when you link this central control into your EV battery charging, into home heating, into your smart domestic appliances, and so on. So these are some of the things we want our smart grid system to do. We want to control our heating to provide adequate comfort where we want it. We want to manage EV charging, so we know that our electric vehicle is charged when we want it. We want to minimise our bills. We want to enable CO2 targets to be met. These are the wish lists. Translating this into engineering is really quite fun. There are also various other things as well. We don't want people to be able to hack it, bearing in mind that if you hack your electricity meter, you could save yourself £1,000 a year. So there's plenty of incentive to hack it. And it would also is likely to be coupled in with all sorts of other networks, so there are plenty of ways in to do your hacking. And it's got to be easy to understand. Here's one of the challenges for it. Imagine you've got a street, this is a simplified street. You've got four houses, each one's got an electric vehicle, and when they come home, that's how the battery states are at any particular time. And there's 4 buttons or something on the battery charger, so when you plug it in, you can say, I want it in an hour, I want it in 6 hours, I want it in 12 hours, or whatever. And the control system, you tell it, what we want you to do is to make sure that, you know, so I'm treating it as a sort of person type thing, this discussion with the control system. We want you to arrange for all the vehicles to be charged when next needed. We want to maximise the use of low carbon electricity, and we want to avoid overloading the cables in the street. So really quite straightforward. And yes, one could do it. It becomes a bit more complicated when you realise that the electricity network operator that owns the cables in the street is a different entity to the electricity retailers that each of these individual houses does business with. So the way that the network has been privatised doesn't actually work very well in this particular state. It becomes more fun when you do other things. Let's assume that all our 4 houses have also got heat pumps. And house number 1, it's already within a degree of the thermostat setting. House number 3, they just switched on, the house is cold, so they obviously want priority here. So again, now you've got your electric vehicles, you've got your electrically powered heat pumps, and you're trying to build a compromise situation that everybody is reasonably happy. Oh, and then you've probably got a few things like this, where somebody loads up their dishwasher and says, great, it's full, now please, control system, will you switch it on at the appropriate time so it costs me the least amount of money? Oh, and by the way, I'd like my things washed by 9 o'clock tomorrow morning. So this is 4 houses. If you can now multiply that up to 40 million houses, that's the kind of challenge that one's looking at for a really intelligent smart grid. And you merge this in with the low carbon electricity, you merge this in with electric vehicles, you merge it in with intelligent home heating. Take this lot together, and then you've probably got a network and a system that will start to get somewhere near this 80% reduction in CO2, and that doesn't actually cost an arm and a leg. There are a few other things you can do if you want to. How do you like vehicle-to-grid energy charging? If you've got a normal situation, you charge all your vehicles, but just imagine the situation where energy is a bit short, electricity is a bit short. You've got one car, the battery is fully charged, and next door the battery is largely empty. Why not ask your computer to say, lend Kevin next door some of my electricity, and by the way, charge him for it? I mean, that might work. Technically, it's possible. Organisationally, it comes into the quite challenging category. And in terms of making sure that it's done in a way that's safe and that doesn't cause problems with electrical protection and other things, again, is not a totally trivial problem. So, a few conclusions. I promised to talk for no more than about 45 minutes, and I think I'm 43 at the moment, so we'll see where we go. The IT has recently put out a report, one of those that's referenced in the papers with this lecture, about the case for a systems architect for the electricity system. I must admit I wrote that paper. It was about it ended up being 30,000 words, and it was really quite heavy going. I think we need actually more than that. That was the need for an electricity systems architect. I believe we actually need joined up thinking and a systems architect for the whole of the energy system, which at the moment we don't have. The idea that somehow markets, untrammeled markets, will provide this automatically seems rather naive. There are various things one can do as individuals. Live near your work and on a bus route. I do that. Send your children to a local school. Walk or cycle, and you might as well campaign for better cycle tracks. Use an electric railway rather than driving. Insulate your house. Have a smart control system. Avoid businesses that use waste energy, and explain. But these really, they're good, but we actually need a bit more than that. And some final thoughts. Firstly, energy policy is difficult. I think a lot of people have come to the conclusion, energy, yes, well, do you know, we've had something like, I think, 30 ministers responsible for energy over the last 40 years or something, and seeing as the time to build anything in energy terms is a minimum of about 5 years, nobody has seen through. I did a blog recently for the conversation saying that the pendulum has to stop in energy policy, and I think that's a situation. We can't have this continual sort of change from saying, yes, we want energy of this form, or we don't want solar panels, we do want wind turbines, we don't want wind turbines. Anybody who says there's a single easy solution, whether it's shale gas or nuclear power or renewables or solar power in the Sahara or whatever, I suggest they don't really understand the problem. That I don't think this is a situation where there's a single answer. What we're looking at is a complicated system that will involve a bit of this, a bit of that, a bit of the other, and putting it all together. So we need this combination: energy saving, renewables, nuclear power, lifestyle changes, and more. One will not suffice, we need the whole lot. And we need a very clever control system. And that, I think, is where organisations like Lancaster University should be able to contribute in a big way. How do we actually put together this type of intelligent system rather than just a simple situation of having a power station and we switch it on when people want to make a cup of tea in the interval of the cup final? So further reading, if you go to that particular anniversary news, find this talk, and there's a little tab at the bottom called Read More, and that will refer you to those papers. Those are the references. Time for a discussion.
Keith Selden, Lancaster City Council. You mentioned hydrogen storage in times of low use for use in when it's needed. And you were talking rather long periods, summer to winter. How practical is this? How much storage space do you need? How much would it cost? And it has to be kept at very low temperatures, I believe. How efficient will it be economically?
I think that's part of the research we need to do. In terms of the efficiency, I'd suggest that if you've got a situation where otherwise you would have to shut down your low carbon generators because you haven't got the load, it doesn't really matter that much how efficient it is, because any storage you can make is a good idea. You're right, it does need to be at low temperatures, it does need to be stored at high pressures. There is quite a loss of energy in the sort of pumping and compressing and cooling to get it down. You can store hydrogen in cylinders at room temperature, very high pressure. I don't know is the answer. People are doing it. I haven't seen the sums. I don't think anybody has really done a serious analysis of what that would be involved. And I think it's work that needs doing.
That was really amazing talk. I quite enjoyed it. One of the key assumptions that you're making in the presentation is the ownership of the car. What if we could, instead of own the car, which is quite costly and inefficient time, because most of the time car is parked in the parking lot instead of using it. So instead of doing that, what if we could adopt an infrastructure where communal car leasing, communal car renting, and that would save a lot of energy in terms of using the car.
Yeah, I think that's a very valid point. There are some issues actually with communal electric vehicle use. You need to charge them somewhere, and provision of charging points on the city street is actually quite expensive. By the time you've got all the sort of necessary smart card readers and everything else, that becomes quite expensive. If you've got multiple users, it may well be that they plug it in and it would end up being charged during the day, so you'd be charging at peak periods rather than charging at night. In terms of energy or carbon dioxide, your best bet is to have as many electric vehicles as possible and only to charge them very occasionally. Now, I agree that's going to be more expensive than having relatively few and sharing them. But so I think there's this dichotomy between cost to the consumer and energy use. And from an energy use point of view, give everybody their own individual car, so you've got lots and lots and lots of kilowatt hours of battery capacity. But if you want to get the more efficient use of the vehicle, then do your suggestion. And how you balance those is one of these difficult questions I think we need to talk about. How's about research, the PhD project on that next year?
Yes, my question is whether, in addition to the engineering and technological solutions or possible solutions that you've talked about, do you think that there's also an important role for political innovations to play a part? I'm thinking, for example, of supposing it was felt desirable to build a light railway from, say, Heysham right up to the university. There's no way that Lancaster City Council, at the present time and under the kind of political arrangements we have at the moment, could raise the cash to do that. And it would be very unlikely that the cash would come from central government. So, I just wonder whether you think that removing obstacles towards more localized forms of raising the capital necessary for some of these energy-saving innovations is also part of the solution.
It's generally much cheaper to get capital borrowed via a government agency than doing it via a venture capitalist who might want 15% return for the first few years. I think our privatisation model for both transport industry and for the energy industries is actually fundamentally flawed. Now, quite how you unscramble all that at this stage, I don't know, but I don't think we're going to see most of the things we've got here while we have this plethora of different organisations running different bits of energy, different accountabilities, different ministers responsible. One needs, even if one uses, and I think one should, private sector to provide the goods, you need this sort of, whether it's a controlling mind, whether it's a system architect or not, I don't know, to basically decide what happens and to put that into an overall workable solution. And I think at the moment that isn't done. I mean, HS2 was planned really on a, well, they've got one and they've got one, we want one too basis. I mean, it may be slightly more scientific, but I shouldn't think very much. The privatisation of buses, well, they didn't sort of mess it up in London because that's where ministers live, but the rest of us had a different sort of set of privatisation structures. I just don't think people have really thought these things through. They do things for political reasons that look good rather than thinking about them hard. I mean, you could even draw the parallel going about international affairs, like what we might or might not be doing in Syria and Iraq, but I'm not prepared to sort of go down that route at the moment.
I don't know if you're aware of the Zero Carbon Britain report that's being produced by the Centre for Alternative Technology. Basically, they've produced a scenario where we can get to 100% carbon reduction, so zero carbon, by 2030, and obviously it's very, very challenging. A couple of the differences to the scenario that you're outlining are that it's done with no nuclear, but it's also done using quite a lot of biogas, synthetic gas, and you mentioned the challenge there is land use. So one of the things you'd need to do would be obviously, and they show a very clear map, if you like, of what we need to do in the future. And one of the main things there is to reduce the amount of meat and dairy that we use, and use some of that land for growing biomaterials.
Yeah, I mean, personally, I'm a bit sceptical about people who say, well, everything, it's very relatively possible to solve it, but we need to change our land use, and we've all got to become largely vegetarian. Perhaps it could happen, but I don't see any particular evidence that that's the way that the mass of the population is thinking. Now, it may be that if you think about smoking, a few years ago, 20 years ago, you would all be smoking, or at least half of you would be, and you'd see the sort of beams coming from the projector up at the screen, like when one went to the cinema in the 60s. Now smoking indoors, even if it's not specifically banned, is considered totally unacceptable. And even in private houses, people go out the back and smoke rather than smoke indoors. So that is a change in culture. Whether we could get the sort of change in culture that you're talking about and that CAT seems to be relying on in that particular scenario, I don't know. If you look at the way that developing countries, China in particular, is going, then they're tending for a more westernized diet, a greater use of meat, a greater reliance on high emissions food, perhaps ideally from both health and environment. They used to say, oh, dear Chinese, please don't do that, please go back to eating rice. I'm not sure that would work. So I think there's some big complicated sociological issues here, and I'm an engineer, and I can see the problem, but I don't claim to be able to solve it.
My question is about the prospects for being able to continue generating enough power in this country. You know, there have been stories that we might be suffering from what they call outages or brownouts or load shedding or something like that, possibly as a result of the government's negligence in trying to pay perhaps too much emphasis on renewables, and it's not worked as well as they thought, and so on and so on. In other words, not enough forward planning. So what's the story? Is it going to happen like it does in other places like India, Turkey, or South Africa, where, you know, outages are a frequent fact of life and it's very bad for the economy?
Yeah, I was one of the sort of reviewers of this document here, the GB electricity capacity margin, which we looked at quite seriously for the it was work that was done for the Prime Minister's Council of Science and Technology. And I think one of the biggest problems is that we haven't invested anything really serious in energy systems. That if you look at the current statistics, anywhere between 20 and sort of 35% of our electricity is coming from coal-fired stations. All but one of those were being commissioned when I was an undergraduate. You know, so if I'm retiring, it's about time they retired as well. And I think that's a sort of that's the situation with coal-fired stations. With nuclear stations, we've got a situation where by the middle of the 2020s, we'll probably have Sizewell B and probably not very much else. As I was trying to show earlier, we cannot rely on, I don't believe we can rely on 100% renewables just because of the intermittency problem and because of the sheer difficulty, as has been pointed out in terms of hydrogen storage. It's not particularly simple to store spare energy. Okay, you can pump stuff up hills, but if you run all the pump storage schemes in Britain at their full power, you'd probably empty the upper reservoirs in about half an hour. So, you know, if you want to do something like that, certainly you have to convert most of the Lake District into a pump storage scheme, which, you know, might be pretty unattractive to some people. So I think there has been a complete neglect of this and a complete failure on behalf of government to actually understand the totality of what they've committed to in terms of reducing CO2 emissions and the issues surrounding the need to replace expired assets. And I think some members of Parliament probably understand that. I don't believe the people who put into law the 2008 Act understood what it was they were actually doing. I could tell a bad story about that, but I won't. And I think there are fairly serious questions about people sort of understanding. At the moment, there is a scheme, there is a capacity mechanism where government, I think, is paying lots of millions, I can't remember how many, £1 million a day, I think is the number that springs to mind, to persuade people not to scrap out-of-date power stations or old power stations, but to keep them ready for 2018. But this is really coming down to a sort of sticking plaster type solution. And just by saying we want to keep these power stations running, 30 years, 40 years, 70 years and 10, I don't know what a power station lasts, but they don't last forever. And we've got a fairly serious problem, I think. There are ways, incidentally, of not having complete cuts. I don't think anybody's talking about saying we will chop off great large lumps of of Britain, you can brown out a bit, you can reduce frequency, you can reduce voltage, you can cut out unimportant places like Kendal and keep important places like Stevenage running, you know, or whatever. But it's going to be fairly close, although probably just on the right side of things as things stand. But I agree that there is an issue. Well, to be honest, I could have gone on for about 4 days on this topic. There is just so much about energy policy. It's complicated, it's difficult, it's got sociology, it's got maths, it's got engineering, it's got ecology. There are a whole lot of questions I can't answer, and I think really what I've left out is what I don't know, and as an organisation we've got to get together and try and put some detail behind all these gaps that we know in the society we just don't at the moment know how to fill.
I think the most interesting thing for me was his conclusion that market forces aren't the answer, which didn't come from a political point of view or an ethical point of view, but just came from a practical point of view.
I came because I'm really interested in how we can power Britain and get to zero carbon as quickly as possible. And I spend all my time on community energy saving and energy generation projects. So I've been involved in building a hydro on balloon and so on. So I'm really interested in different scenarios for how to get there. And, you know, he's come to different conclusions than Centre for Alternative Technology, for example.
The title actually sort of attracted me, so scrap the car to save the planet. And I'm a very ambitious person in a way that I want to, this climate change is a very global problem, it's very, very complex. And I'm the young person, so this is going to be my problem in the future. So I want to solve this somehow, and then the title sort of gave me the incentive to come.
And I just find it really interesting at this point, those different perspectives. He clearly comes from an incredibly experienced point of view. And informed, yeah. So, you know, I found that I'll listen to people who know what they're talking about, even if they've come to conclusions that I don't agree with, forever, because, you know, somewhere in there is some real truth, as well as potentially, you know, an opportunity to challenge that and to come to a different conclusion.
Well, we're a university, we're in the middle of a city, we basically need to let the city know what we're doing, what we're thinking.
To have that knowledge shared with a wider community and not just students here, you know, for me it's absolutely invaluable. I come to lectures here a fair bit because I want to hear that expert opinion.
I hope the university do more of these talks in the future.
Oh, I enjoyed it. I thought the audience were fantastic. There was such a great variety of people. There were some students who actually probably have seen most of the slides before, to be honest. And then there were people who were from U3A, from various religious societies, from the Green Party, from all sorts of places. And I think it was great to bring together this great collection of people.